Now let's start with this example. Is the series from 1 to infinity of 2 to the n over 3n plus 1 convergent or divergent? So here what it looks like is when n is 1, you get 2/4, so that's 1/2, and then you add, when n is 2, you get 4/7, so you have 1/2 plus 4/7, then when n is 3, you get 6/10, so you add 6/10, and you keep going this way, and you want to know if it's something convergent or divergent. So what kind of analysis can we make here? We have this sequence of terms, right? 2n over 3n plus 1, and we're going to add them together. The first observation here is that the sequence of terms itself is convergent. Of course, it has nothing to do with whether, well, we'll see that it has something to do, but it's not the same question as to whether the sum of these terms is convergent, but the sequence of terms itself is convergent and converges to the number 2/3. That's because top and bottom are both polynomial in n of the same degree, so the limit is the quotient of the leading coefficients. And so that means that for the indexed n sufficiently large, say greater or equal to some capital N, the term an equal 2n over 3n plus 1 can be made as close as we want to 2/3. In particular, we can make sure that it is greater or equal to 1/2. But that means that when I'm adding a large number of terms of the sequence an, then I'm adding at least, I'm adding the first few terms, those before this capital N, and then the terms from capital N to my little n that is larger, and that I think of as very large. The first sum is a finite number, whatever it is. The second sum depends on n, and we're going to look at what happens when n grows. So I have this sum of ai's where each one of the ai is greater or equal to 1/2, and I add n plus 1 minus capital N terms. Each one of them is at least 1/2. So I get something that is greater than this finite number, the sum from 1 to capital N minus 1 of the ai's, plus 1/2 times the number of terms that remains, which is n plus 1 minus capital N. And you see that as n grows, this is going to go to infinity. So that means that because the limit of this term is infinity as n goes to infinity, and Sn is greater than that, then the limit of Sn must be infinity, and that means the series is divergent. Now, this is a particular case of a more general observation that if we have a convergent series, then the limit of its terms is 0. Right? The sequence of terms that we're adding together must be convergent and convergent to 0. So how do we prove that in general? If the series is convergent, it's really saying that the sequence of partial sums, so adding the first n terms together to define the nth term in my sequence of partial sums, Sn, this is a convergent sequence, and its limit is what we call the series from 1 to infinity of the n. So let's call that L. This is some finite number. Then note that Sn, the sequence of partial sum, is the sum of the first n terms in the sequence an. So it's a1 plus a2 plus a3 and so on until an. But if I add all the first n terms and I subtract the first n minus 1 terms, then everything cancels out except the nth term an. So one way to write an is as the difference Sn minus s indexed by n minus 1. And therefore, the limit of an as n goes to infinity is the limit as n goes to infinity of this difference Sn minus Sn minus 1. But since the sequence Sn is convergent, then Sn and Sn minus 1 are two sequences that are convergent and convergent to the same limit. And then the limit of a difference is the difference of the limits. So I obtain the limit of Sn minus the limit of s indexed by n minus 1, and of course both sequences have limit L, so the difference is 0, and that means the limit of an, which is this difference, is 0. So we've proved that if we have a convergent series, the sequence of terms necessarily converges to 0. One way to rephrase this is that if the limit of the sequence of terms is not 0, then the series is divergent, for otherwise it would be convergent and therefore the sequence of terms would have limit 0. But this is often this so-called contrapositive form, the second form that we use in practice as a criterion for divergence. So for instance, if you consider the series from 1 to infinity of arctangent of n, you can immediately conclude that it is divergent because the limit of arctangent n as n goes to infinity is pi over 2. And this is not 0, so the sequence of terms doesn't go to 0, so the series is divergent. Similarly, if you were to look at the series from 1 to infinity of n plus 1 squared divided by n plus 2, then you look at the limit of the sequence of terms. You have a quotient of two polynomials in n. They are both polynomials of degree 2. They are both with a leading coefficient of 1, so the limit is 1 over 1, 1. And this is not 0, therefore, when you add together these terms, right, the corresponding series of general term n plus 1 squared divided by n plus 2 is divergent. Now the thing to remember about this is that the converse is false. In other words, if the limit is not 0, then you can conclude that the series is divergent. If it is 0, well, you cannot conclude anything. It's not enough for the sequence of terms to have limit 0 for the corresponding series to be convergent. It is not enough. This is very important and one of the most common source of errors on series. So keep that in mind. There are sequences that have limit 0, but when you add together the terms you get a divergent series. Of course, here I claim that there are such sequences. You might want to see an example. So let me provide you with one. A very simple one. The series from 1 to infinity of 1 over n is divergent. There are various ways we could justify that, and here I'm going to use an argument that we will revisit when we discuss the integral test. Let me look at the partial sum for this series. So I'm adding 1 to 1/2 to 1/3 and so on until 1 over n. And I want to see whether this is a convergent sequence or not. In fact, I'm going to show that it is a divergent sequence. And I'm going to do that geometrically. What I'm adding is the terms of 1 over n, which are particular points on the graph of 1 over x. And I'm going to represent this in a particular way. I'm going to represent the first term 1 as a square whose base on the x-axis goes from 1 to 2, and height corresponds to the value of the function 1 over x at the leftmost endpoint of the interval, in other words at 1. So the height is 1, the width is 1, it has area 1. 1/2 is going to be represented by another rectangle. The base on the x-axis goes from 2 to 3, and the height is given by the value of the function at 2, which is 1/2. So I have something of width 1, of height 1/2. It has area 1/2. And then I keep going that way. I look at a rectangle whose base goes from 3 to 4 on the x-axis, and the height is given by the value of the function at the leftmost endpoint of the interval. In other words, at 3, and therefore it has area 1/3. And I can keep going this way. So in this particular picture, I have just added 1 plus 1/2 plus 1/3 plus 1/4. And you see that this red area is above, the sum of the area of these rectangles is above the area under the graph of 1 over x over the interval running from 1 to 5. Right? So if I add the first 4 terms, I get something that is above the area under the graph of 1 over x from 1 to 5. If I was to add one more term, adding the first 5 terms, I would get an upper bound for the integral of 1 over x from 1 to 6, and so on. So what we have is that the partial sums adding the first n terms is greater or equal to the integral from 1 to n plus 1 of 1 over x. And that we know how to calculate, because an antiderivative of 1 over x is natural log of absolute value of x, that we evaluate from 1 to n plus 1. At 1 this is 0, so we get just natural log of n plus 1. But the limit as n goes to infinity of this is infinity, because the limit of the natural log at infinity is infinity, and therefore Sn, which is greater than something going to infinity, must go to infinity as well. So if the partial sums go to infinity, that means the series is divergent. So you see that here the sequence of terms 1 over n goes to 0, but the series of 1 over n, when we add together the terms, is divergent. Now turn to the next video for more details.